We talked about, this is, as I mentioned, and you'll see it today, I'll prove it to you, this is the most technical part of the whole lecture. So brace yourselves. What we're going to do is we're going to derive constraints for multiple views. So we derive the epipolar constraint, from which we then develop the 8-point algorithm. And in this chapter, we're going to extend this to multiple views, and we'll focus on points observed not in two, but in multiple views. And this is what you see in this equation. This equation describes the observation of points, and the 2D points are x1 through xm. It's basically one point, large X, that is observed in multiple views. Right? And we have these projection matrices that model the projection of that point, large X, into m different views. So not two. With the epipolar constraint, we would just have two lines here. Here we have m lines, m observations of a point large X. And these observations in the 2D images are called x1 through xm. And here are the unknown distances, lambda 1 through lambda n. That is the distance to the point large X. And you remember, if we take the 2D coordinate and scale it with its steps, if it's in homogeneous coordinates, then we get the 3D point. But up to obviously the camera transformations that are encoded in these pies. And this is very general. Often we took the view where we said the first camera is the reference coordinate system, but here we can have world coordinates, and the first camera can have its own rotation and translation. So this is the equation, and if we write it in a very compact form, we can call this matrix I, this vector lambda, this matrix pi, and then x. And what we do now, we rearrange this. Basically, you see pi and I we put into one matrix, and then basically we have the constraint pi I times this vector x minus lambda equals 0. Right? So what we do here is we take everything to the left-hand side, I lambda minus pi x equals 0, and then we write this pi I into one matrix, and then x transposed minus lambda transposed into another vector, and then we have this matrix, call it np times this vector u, must be 0. So this equation here is the same equation as on the previous slide. Yes, so we wrote it in one equation. Why do we do that? Well, now we can interpret, we can say, oh, this matrix NP, this is this matrix, this is a matrix that has a vector in the null space. And that is a non-zero vector because it contains the depth values and the 3D coordinates. And what's interesting here is, again, in this way we separated the 3D coordinates and the depth values from the camera coordinates. So this matrix NP, you can see it, it only contains the camera transformations and the 2D coordinates that we know they're given. And so now we can say, since this vector u lives in the null space of this matrix NP, the rank of this matrix cannot be full rank. All right, so this vector u is in the null space, and that means the matrix does not have full rank. And here you see, this is something I found interesting. We talked about the rank of matrices in the introduction to linear algebra. When I learned about ranks of matrices, I thought that was a completely useless concept. It is not. You can actually do things with it. You can say, here, for example, we have a matrix that is of dimension 3m times m plus 4. And so the rank can be at most m plus 4. But if the rank is m plus 4, then it has full rank. Then the null space is only the 0 vector. Right? And we can argue, since there is a non-zero vector u in the null space of this matrix NP, the rank cannot be full rank. And since the rank is at most m plus 4, it means if it's not full rank, it must have rank at most m plus 3. And more specifically, and we'll use that later on, we can say if there is a unique reconstruction, there must be a 3D point x and depth values lambda, such that this vector is mapped to 0 by this matrix. If that vector exists, then the rank is m plus 3 of the matrix. And if that vector should be unique up to scaling, then the rank should be not less or equal to m plus 3, but exactly m plus 3. Because if it's less than m plus 3, maybe m plus 2 or m plus 1, then it means the solution is non-unique. And this is how you can use the rank and look at the rank of this matrix, and it will tell you everything. If the rank is m plus 4, that means there is no solution, no vector that lives in the null space. If the rank is m plus 3, there is a unique solution. And if the rank is m plus 2 or less, then there are potentially multiple solutions. Then there is no unique reconstruction. And so just by computing this matrix and looking at its rank, we can basically define the number of solutions from none to a unique one to infinitely many. And so what we're going to do is basically we're going to say this is the matrix NP. The camera transformations between the various images must be such that the rank is exactly m plus 3. And this is how we can constrain what kinds of camera motions are conceivable with these multiple views of a point. And so this is much like the epipolar constraint, which tells us about what camera motions are conceivable. Here we have a similar one. And the constraint should be, the rank should be m plus 3. Now this is a little bit tedious. Oh, and then we rewrote this in the following way. We defined this matrix I bottom, where we have on the diagonal x hat, x1 hat through xm hat, and it has the property of what's called annihilating I. Remember, I was this matrix here, this one, with the xi's on the diagonal, and xi hat is always such that xi hat times xi is 0. So if you define this matrix with the xi hats on the diagonal, it has the property of basically killing xi. And so if we pre-multiply the above equation with I bottom, we get, I bottom times I is 0, and I bottom times pi is not necessarily 0, and so what we end up with is basically this equation. I bottom times pi times x equals 0. So this is a rewrite. This can be deduced from applying this matrix. And so it means we have a matrix I bottom times pi that has a vector x in its null space. And since that is the 3D vector encoding, the vector encoding the 3D point, it's not a null vector, so there is a non-trivial vector in the null space of this matrix. And this is what we call WP, is this matrix. I bottom times pi, and since I bottom has on the diagonal these xi hats and pi has on the diagonal the pi i's, we have xi hat times pi I on, stacked into this matrix here. And what dimension does it have? Again, you'll see we always compute these matrices and then we look at the dimensions they have. It's a 3m by 4 matrix. And now we're saying this matrix has a non-trivial null space. There is a vector x in the null space, and obviously we want this vector to be unique up to scaling. So the null space should be one-dimensional, and so the rank for a unique reconstruction should be 3. If we allow multiple conceivable reconstructions, then we can say the rank should be at most 3. Why? Because it has rank 4, by default it has 4 columns, so the full rank would be 4, but if the null space is not just the 0 vector, then the rank must be at most 3. So this comes in over and over, this arguing about ranks of matrices. And it's a fairly popular concept in the natural sciences when dealing with linear algebra techniques, that you look at matrices and you look at ranks of matrices, like here. And so we see, we now talked about the matrix NP and the matrix WP, and we showed that the matrix WP has a rank that is the rank of NP minus M, and that is 3. So you see, we simplify things a little bit, so we have a matrix with 4 columns, and we say this matrix should have at most rank 3. We can interpret this constraint geometrically. We can say the point X lives in the null space of this matrix. And basically, if we look at this matrix, it defines a set of planes, in fact 2 M planes, I think I mentioned that last time, and the constraint says that the point basically lives in the intersection of all these planes that you see here. So this is the point observed in image 1, this is the point observed in image 2, and this is the geometric interpretation of this rank constraint. What we're going to do now is we're going to rewrite this even more compactly. If we go back, what did we derive? We first constructed a huge matrix that is 3m by m plus 4, and we said its rank is at most m plus 3. Then we constructed a more compact matrix, I bottom times pi, that we call WP. And we said it's a 3m by 4 matrix, it has at most rank 3. And now we're going to compactify that even further. You'll see in a second, basically. And you see, in order to do that, we go into the coordinates of the first camera. So the projection matrix for camera 1, we assume, is just the identity of rotation and no translation. So the world coordinate system is the system of camera 1. And then we have the remaining cameras with rotation and translation here. And these are 3 by 4 matrices. And they model the projection of a point X into the individual images. And then we can define this matrix WP. Here it is. And now we'll do something that at first glance looks a little bit weird. We take this matrix WP and multiply it with this matrix DP, this one here. This is a 4 by 5 matrix, and what's important about this matrix, it's a matrix that has full rank. Why does it have full rank? As you can see, it has 5 columns. No, 3, 4, 5 columns. And basically what you have here has and 4 rows. So it's a matrix that has at most rank 4. But it has here 4 independent columns, as you can see. This one is a rank 2 matrix, this X hat. These hat matrices, we talked about it, they always have rank 2, unless they're 0. And this is a vector, x1, that is actually orthogonal to the vectors here. So it defines another it adds one more to the rank, so this together gives it rank 3. And then here we have a 0, 1, so we have a component here that creates, basically is linearly independent from the other columns. And so this has 4 linearly independent columns, and that basically entails that you can look at this matrix and you'll see it has the rank 4. And that means it's a full rank matrix. And why is that important? we mentioned that in the linear algebra section. If you multiply any given matrix with a full rank matrix, then the product will preserve the rank. Multiplying a matrix WP with a full rank matrix does not affect the rank. So if WP has a certain rank, WP times DP will have the same rank. And if you do this multiplication, it's a little bit tedious to do, quite honestly. But I did it, I verified, and indeed what you get out looks like this here. And I should say at a first glance, who comes up with these ideas? I don't know. I don't know who came up with this idea, but it's a technique that I read about in this book of Ma and Soato and Koseka Sastry. It's quite a clever trick, because what you end up with is this big matrix here. And then you can argue, since there are zeros here, this is how it was designed. So this matrix is designed so that on the top you have zeros here. And here you have x1 hat times x1 hat. And now you can argue the whole matrix here, and this is two column vectors here. And you can argue this whole matrix has rank at most 3 if and only if this submatrix here has rank at most 1. And that is because this matrix contributes a rank of 2. So if this here had more than rank 1, then together with this it would have more than rank 3. This is the argument here, right? It's a little bit tricky, but the argument is that since this already provides a rank of 2, x1 hat has a rank of 2, right? And x1 hat times x1 hat also has the rank of 2. So this structure here contributes a rank of 2, and then this remainder can only contribute 1 more in terms of rank. And so you can deduce that this matrix down here, this submatrix, this one, let's call it MP, this must have rank 1. And this matrix, these are 2 column vectors, right? So this matrix is a 3 times m minus 1 times 2 matrix. So it has 3 times m minus 1 rows and 2 columns. And these 2 columns must be linearly dependent. That means one must be a multiple of the other. And this matrix has rank 1. That is the constraint. So this constraint in green, rank WP lesser or equal to 3, is equivalent to saying the rank of MP is lesser or equal to 1. And so now you see how we further compactified it. Now we have an equation that contains, what does it contain? The 2D coordinates in the images and the rotations and translations for each camera, R2, T2, R3, T3, and RM, TM. And this matrix has 2 columns and they are linearly dependent. This matrix has rank at most 1. In fact, you can argue if the rank of this matrix was 2, then there exists no feasible reconstruction. If the rank is 1, exactly 1, then there is a reconstruction that is unique up to scaling. And if the rank is 0, that means the matrix itself is 0, then you have non-uniqueness in the reconstruction. And so just by looking at a matrix with 2 columns, you can tell from the 3 cases on the rank, a matrix with 2 columns there's only 3 possibilities for its rank. It could be 2, 1, or 0. And that distinguishes the 3 cases of, no reconstruction, a unique reconstruction, and multiple reconstructions. And so to summarize, the study of looking at projections of a single point large X projected into multiple images, we can construct this multi-view matrix, it's called, a matrix with 2 columns, and And we can say we can construct different matrices, but this matrix has a rank that is the same as rank WP minus 2, and the rank of WP was the rank of NP minus M plus 2. And all of these matrices have a rank bounded by 1 in order to have a reconstruction. And they have a rank exactly 1 if the reconstruction should be unique. So for multiple images of a point, we have these 3 matrices, and if it's a single point that is projected into multiple images here and that we observe in these images, then these rank constraints must be fulfilled. We can again interpret this geometrically. So here is the multi-view matrix again. And what does it say? So there's 2 columns in this matrix, and this matrix basically we're saying the rank should be at most 1. And that says nothing but if you have 2 vectors, it means one vector is a multiple of the other. So this vector here is a multiple of that vector there. That's what it means to be linearly dependent, and that's what it means to have rank less or equal to 1. And in fact, this mimics the projection, basically, the projection of the point into image I can be written in this way. We've seen that. Lambda I, if we take this point and rotate it into the coordinates, wait a second. So these are the projection equations. We derived them earlier here. Lambda I xi hat ri x1 plus xi hat times ti equals 0. That's basically saying that this, if this column is a multiple of that column, it means this thing is a multiple of that thing. And then we can define a vector lambda 1, a scalar lambda 1, such that lambda 1 times xi hat ri x1 equals x plus x2 hat t2 equals 0, right? This is saying they're linearly dependent. Right? You remember the definition of linear dependency was that there's a linear combination of the 2 vectors that maps to 0. Here it is. And if you write that out, you can say MP times lambda 1, 1 is 0. Now you could argue, why did we call the factor here lambda 1, this scalar factor? It is actually the distance of the point from the first camera. And so what it captures, this multi-view constraint, what it captures is that there exists a distance. And this is the distance of the point from the first camera that is not observable from just that first camera, but that becomes observable once you have multiple cameras. So, and that is the information about the point that is missing in the first image, right? If I see a point in the first image, then I know the 3D location should be along this ray. But what I don't know is how far it is. And this information is captured in this constraint, that there is this physical distance of the point 1, the point from image 1. How does that relate to the epipolar constraints? We now have these constraints for multiple images of a point observed in multiple images. How does it relate to the epipolar constraints that we had for 2 images? Here's the matrix again. For this matrix to have exactly rank 1, it basically means this vector and that vector must be linearly dependent, as we said. And that basically means this thing must be a multiple of that thing. And this actually corresponds to the epipolar constraint between image 1 and image 2 for the first pair, and image 1 and image 3 for the second pair, etc. And we'll see why that is on the next slide. But what's more is you could say, okay, if this thing is a multiple of that thing and this thing is a multiple of that thing, you could say, well, then it's nothing but all the epipolar constraints between the first camera and the eye's camera. But the truth is there is more in this constraint than just epipolar constraints. And the information that is in there is that not only is this block here on the top, this thing, a multiple of that thing, or there's a linear combination of these two that maps to 0, but there is a linear combination of these with the exact same factors that maps to 0. So it's the same lambda 1 that models this linear dependency. And this is an additional constraint that is not trivial. So it's not just one being a multiple of the other, but it's one being a multiple of the other with the same factor for all of these blocks that you have here. So let's look at this. I'm claiming that, but this being the linear combination of these two elements corresponds to the epipolar constraint. Let's look at how that works. So the claim was that linear dependency of xi hat ti and xi hat ri x1 gives rise to this epipolar constraint xi transpose Ti hat Ri x1. See, this is the epipolar constraint between image 1 and image I. Sorry, this doesn't work super well to highlight. So, let's prove this. Here's how it works. Assume we have these two vectors, xi hat Ti and xi hat Ri x1. We're saying there is a scalar such that one is a multiple of the other. Let's call this scalar gamma. Now xi hat is nothing but, xi hat ti is nothing but xi cross product with ti. And remember that is a vector that is orthogonal to xi and ti. Whereas this one here, xi hat ri x1, is a vector that is orthogonal to xi and ri x1. So we have three vectors here. They are xi, ti, and ri x1. These three vectors. And these vectors are such that if I do cross products between pairs of them, I get the normal vectors, and these are coplanar, the two normal vectors. So if I, this vector here is a vector that is pointing in the normal of the plane spanned by xi and ti. So xi and ti span one plane, and that it's normal. And xi and ri x1 span another plane, and this is a vector pointing in the normal of that plane. And now saying one vector is a multiple of the other means it's the same plane. And it means these three vectors are coplanar. They all live in the same plane. And if you remember our discussion in a chapter on the epipolar constraint, we proved that this is exactly the epipolar constraint. It says that these three vectors, maybe I should draw a picture, these three vectors actually form the same plane. And so we have now kind of deduced that this equation that says one is a multiple of the other corresponds to the epipolar constraint between the two images. And the fact that these three vectors form a plane can be rewritten in this way. We've seen it before, and that is exactly the epipolar constraint. So here's the point large x, here's the observation in image 1, so this is x1, and here's the observation in image, what do we call it? I, right? So this is xi. And then we have a rigid body transformation, and we can define this system. And basically the statement is that these vectors that you have here, this one is xi, this one is t, the translation vector here, basically this one, and then we have this vector here, and in the coordinates of the i's image, this is ri times x1, because you have to rotate into the coordinate systems of the first camera with the rotation ri. This is ti, right? And basically the statement that we have now is that these vectors, they form a plane. So this vector, and this vector, they all live in a plane, which implies that there is an intersection here. Because if they don't live in a plane, then you don't have any 3D point in the intersection. So it's again this epipolar constraint that we can read out. But there is more. So this matrix, here it is, MP, as I said, it has two columns, right? And one column is a multiple of the other, because the rank is at most is 1, so 1 is a multiple of the other. And if we write these two columns like this, so 1 is a column with A1 to AN and B1 through BN. I don't know why I call it N, it should be M probably. Yeah, it doesn't matter. So it doesn't matter. So there's two column vectors, non-zero. And now we're saying one column vector is a multiple of the other, meaning the rank of this matrix is 1. And now there are several statements you can make. And there is one statement. What we now showed is that if AI is a multiple of BI, then that entails the epipolar constraint between image I and image 1. That's what we just showed. We'll show that there is more in this constraint, though, than just the pairwise epipolar constraints. So, we have this image I, and we have, lots of images. And in principle, we can say we have epipolar constraints always between the first image and the second, the first image and the third, the first image and the fourth, etc. But we'll show now that there is more information captured in these multi-view constraints. In fact, what you can show is that this matrix with two column vectors of this form is rank deficient if and only if these expressions are 0. AI bj transpose minus bi aj transpose is 0 for all pairs of I and j. This is a statement that is a bit technical to prove. It's a general statement in linear algebra. We're not going to prove it in this class. It's a general property for matrices of this form, that they are rank deficient if this holds. As another example, right? If you ever, have a class on linear algebra and someone were to prove this statement to you, you would likely say this is a completely useless statement, right? But turns out no, and it's amazing how many things people in linear algebra proved, and some of them turn out to be very useful. And this is one, because what we can do now is we can take this statement from linear algebra and we can basically rewrite the rank constraint into these so-called trilinear constraints. Why are they trilinear? Because if we write that out for our matrix, right? Our matrix, where is it? Here it is. AI involves x2 and x1, and BI involves x2. And now we have the statement AI bj transpose minus BI aj transpose is 0. If we write that out, then this is what it looks like. This is the expression here, right? It's a little bit heavy, lots of symbols here, but what's interesting is that each of these terms involves 3 points, namely the point x1, the point xi, and the point xj. So I now have a constraint that always involves triples of cameras, triples of observations. The epipolar constraint, remember, was a constraint that involves pairs of observations, image 1 and image I. Here now I have a constraint that involves 3 points simultaneously and also the motions between the 3 cameras. Namely, the rotation between the first and the I's camera, and the rotation between the first and the J's camera. And if I rewrite this out, you can multiply this out, and then you see you have xj hat transpose on the right. If you do the transpose, you have to invert the order here. And so you can pull out the xj hat, and you can pull out the xi hat on this side. There is no transpose. Why? Because these matrices x hat are skew symmetric. So x hat transpose is the same as minus x hat. And we use this property, and this changes the signs basically, and then you end up with this equation. Or more specifically, you get an overall minus sign by doing this transpose, and so you can rewrite it this way. And this is a matrix equation, so it corresponds to 3 by 3 scalar, 3 times 3 scalar trilinear equations. And in fact, one can show that only 4 of them are linearly independent. I'm debating how much deeper I should go. As I mentioned, this is a rather technical chapter, and I just wanted to give you an idea here of how this works. So one can study these constraints. And look at what they say. They actually contain the bilinear epipolar constraints, except for degeneracies. So you can basically if these entries here, xj hat t and xj hat this one here, if they are as long as they're non-zero, you can deduce that the 2 vectors xi hat ri x1, this one here, and this one here, that they're linearly dependent. And that, remember, is basically the epipolar constraints. And so we can read out again the epipolar constraints. And what's nice is that we can rewrite this rank constraint that we derived first. It's actually equivalent to these bilinear and trilinear constraints. So here's where we left off. We discussed the projection of point observed in multiple images, so not 2 but more than 2 images, as a way to generalize the epipolar constraint that was derived for the 2-image case. Here now the multi-image case, so we have observations of that point in m images. These are called little x1 through little xm. And then we have corresponding camera motions between the different cameras, relating the second camera to the first camera, the third camera to the first camera, etc. So these are R2, T2, R3, T3, rotation and translation of the eye's camera into from the first one. And then we derived constraints saying that if there is a point in the intersection of the various pre-images, then the rank of this matrix must be 1, or it must be bounded by 1 for there to be a feasible reconstruction. So we have rank of this matrix MP being bounded by 1. This matrix has 2 columns of length 3 times m minus 1. So obviously with 2 columns, it will have at most rank 2. And the constraint says it should be at most rank 1. And that essentially means that one column must be linearly dependent with the other one, meaning there is a linear combination that maps them to 0. And that means there is a two-dimensional vector with coordinates lambda 1 and 1, such that MP times this vector must be 0. And so in some sense, this rank constraint really captures the unknown distance lambda 1 of the point P that we're looking at from the first camera. And this information, this distance from the camera, is missing from one single image, but it is, as you can see here, contained in the observations from multiple images. Next, we showed that one can derive the planar epipolar constraints here. So for this matrix to have exactly rank 1, the 2 vectors must be linearly dependent, and that means that one must be a multiple of the other. And as we've seen, next slide here, so if one of these vectors, xi hat ti, is a multiple of the other with some factor gamma, this entails the epipolar constraints, something we've, because basically it says that it all comes down to saying that these 3 vectors, xi, ti, and rix1, all live in the same plane, meaning they're coplanar. And that, you remember, is, if I have these 2 observations of a point, here's the vector connecting the optical centers is the translation vector, and then the 2 xi's. Xi is one, Rix1 is the other one in the coordinates of the I is 1, then saying this basically says they all span a plane, and that entails that there is a point in the intersection of the 2 observation vectors. But there is more information contained in this epipolar constraint than just there's more information contained in this multi-view constraint, saying rank MP should be 1 or less or equal to 1. Than just the epipolar constraints. And this is what we'll see here. And for that, we'll make use of a property of a result from linear algebra. And that is a result that applies to any matrix with 2 column vectors, A1 through AN and B1 through BN. And the statement says that this matrix is rank deficient if and only if we have these properties AI BJ transpose minus BI AJ transpose must be 0. This is a statement that will not prove here from linear algebra, but we'll just make use of it. And if we do that for this matrix, if we write out these constraints for this matrix, and as you can see, they always involve one element from the first column, so AI, BJ, BI, AJ, these are 4 different elements from these 2 matrices. If we write that out, then we get this constraint. It's a somewhat lengthy constraint, but let's look into it. It contains, again, 2D observations of points in the first image, in the I's image, xi, and in the J's image, xj. And it contains corresponding camera matrices, rotation and translation relating always the I's and the J's image to the first image. And so this is called a trilinear constraint. Why is it called trilinear? Because it's linear in 3 elements, right? It contains the elements of the observations of points in 3 cameras rather than 2 cameras.
And this is a very important observation here. The fact that this multi-view constraint, which in principle contains information of a point observed in M images, for this multi-view constraint to be fulfilled, it is equivalent to having these trilinear constraints fulfilled. So constraints that only couple 3 images at a time. And that's a surprising observation. It basically means that once we have information about 3 images at a time, it doesn't actually provide any additional value to consider 4 images or 5 images at a time. So if we consider all conceivable triplets of images and we impose these constraints, that is as much as we can extract in terms of information from multiple views. So we'll see that the trilinear constraints contain more information than just the pairwise epipolar constraints, but it also basically implies that considering more than 3 images doesn't provide additional constraints. So these trilinear constraints, they basically form a matrix equation, and it's a 3 by 3 matrix, so it's 9 scalar trilinear equations. We'll analyze these now and we'll look at what they contain in addition to the bilinear epipolar constraints. So first observation is if these entries here, these are vectors xj hat tj, and this one xj hat rj x1, if these are non-zero, then basically this entails that these 2 vectors are linearly dependent. Why? Because there is a linear combination here of these 2 vectors that maps to 0. If, on the other hand, both of these are 0, this could happen. It's a rare degenerate case where xj hat tj is 0, that is the cross product of xj and tj. And this is the cross product of xj and rjx1. And, the cross product is 0 if the vectors are parallel, because the cross product is basically a vector normal to these 2 vectors, right? But for this to be 0, it means they all lie on a line, right? And that happens in the degenerate case that the point P that we observe from these 2 cameras lies on the line through the optical center. So you have these 2 camera centers, and if the point you're looking at is exactly on this line, it's a very rare case, but in theory could happen, then we have a degeneracy. But except for that very rare degeneracy, the bilinear constraints relating the 2 views are already contained in the trilinear constraints. Why is that? Well, because the fact that these 2 vectors here, xi hat rix1 and xi hat ti, the fact that these are linearly dependent, we saw that earlier, it actually is equivalent to the epipolar constraint. It is equivalent to saying that these 3 vectors, the translation vector xj and rjx1, that these 3 vectors, they form a plane. And that was nothing but the epipolar constraint. One more observation is that the equivalence between the bilinear and trilinear constraint on one hand and the condition that rank of MP is bounded by 1 on the other only holds if these vectors in MP are non-zero. Here, these 2 column vectors that we have in this multi-view matrix MP, if they're non-zero. If they're both 0, this is a very rare degenerate case, then it doesn't entail these bilinear or trilinear constraints. Now, we always are aiming for the case that we have a unique pre-image, so that there is a unique point in the intersection of the various pre-images. And what we can now do is show how the bilinear and trilinear constraints that we have here assure the uniqueness of a pre-image of a point observed in 3 images. So let's say x1, x2, and x3 are the 2D point coordinates in 3 camera frames with distinct optical centers. So this is important. The camera actually moves from one location to the next. For example, all of this would not work if you just rotate a camera with the optical center in the same place. You have to have distinct optical centers to have this parallax that will allow you to infer a meaningful 3D point. If these 3 images satisfy the pairwise epipolar constraints, then a unique pre-image is determined, except if the 3 lines associated to image points x1, x2, and x3 are coplanar. So let's look at that. What is and here these Tij and Rij refer to the transition between frames I and J. So we have 3 frames, 1, 2, 3, with indices Ij can be between 1, 2, and 3. And then we have these epipolar constraints between pairs of images. This degenerate case that we mentioned here, that the 3 points are coplanar, let's look at that. That would be this case here, right? So here are the 3 optical centers. They're in general position, right? They form a plane. This is the so-called trifocal plane. And now we say the point P that we're looking at lives in the plane spanned by these 3 optical centers. If that is the case, then as you can see here, in pairs of images, there's always an intersection of the observations, say, for example, camera 1 and camera 3 here. There is also a point in the intersection for camera 1 and camera 2 and camera 2 and camera 3, but these 3 points need not be the same. So I have basically 3 points in the intersection of pairs of rays, but they need not be the same. And this is quite a rare or rather seldom setting that the point I'm observing happens to live in the same plane spanned by the 3 cameras. And that is then a degenerate case where I cannot expect to uniquely reconstruct the point. Fortunately, that setting doesn't happen very often. Similarly, if these vectors satisfy all trilinear, and so here you see this is an example where the pairwise epipolar constraints are not sufficient to assure a unique pre-image, right? It basically means if I just impose pairwise epipolar constraints, I cannot be sure that the point P is unique. Defined by these epipolar constraints, because I can have 3 different points P such that the pairwise epipolar constraints are fulfilled. But we'll see that the trilinear constraints are actually stronger than the epipolar constraints. So if these 3 vectors satisfy all trilinear constraints of this form, then a unique pre-image is determined, also in the case above. In this kind of pathological case, it is determined unless the 3 lines associated to image points x1, x2, and x3 are collinear. So not coplanar, but actually collinear. That is this just to say collinear means they're along the same line. This is a very rare case. When can that happen? So there's one case where this can happen and actually does happen in practice. And that is a case where in the context of autonomous driving, let's say, if you're driving down the highway in a straight line, then all camera centers live on a line. And then if you observe a point right where you're moving, the focus of expansion it's called, then you can imagine that all these observations, they are all collinear. And that is a degenerate case where you cannot recover the 3D position of that point that you're moving to. Any point along the ray in your direction of motion will be a valid reconstruction. And it doesn't matter how many observations you have along this line that you're moving. So if you're really moving along the line and looking along that line, this is a clearly degenerate case. So these are two statements about the uniqueness of the pre-image that we can expect from the epipolar constraints and from the trilinear constraints. It kind of shows you that you have a better way to impose a unique pre-image by looking not at just pairs of images and their epipolar constraints, but by looking at triplets of images and the corresponding trilinear constraints. So this is one degenerate case that we discussed, where we have pairs of epipolar constraints from 3 cameras, but since the point P is in the plane spanned by these 3 cameras, we don't have a unique pre-image from the epipolar constraints. Here is another degeneracy. For the pairwise epipolar constraints. This is an example where the optical centers lie on a straight line. So for example, as I mentioned, the case when you're driving down the street. And then even if you're not looking in the direction you're driving, but out to the side window, let's say, and you observe some point there, then you know, since the optical centers are on the line, for any point that you observe, no matter where in 3D space, then the optical centers together with that point will form a plane. And then again, as you can see in this example, you will not have a unique pre-image just by considering pairs of lines. You consider pairs of lines, say x1 and x2, you say there should be a point in the intersection. You consider x1, x3, you say there should be a point in the intersection. And then x2 and x3, again, you impose the epipolar constraint saying they should intersect these lines, right? So you impose all the possible epipolar constraints and still you do not get a unique pre-image necessary. So this is a case where the point P and the optical centers again live in the same plane, and that is not so rare. It happens when, say, a car moves on the highway, when an object moves in a straight line. And then for these cases, the epipolar constraints will not allow a unique pre-image, both in this case and in that case. Right, so this is rare because it means only very specific points will fall into this category. But this case is more common because it happens frequently that the moving camera moves on the line. And then you can run into trouble by imposing just the epipolar constraints. But for both of these constraints, the trilinear constraints, so considering triplets of points, will assure a unique pre-image. As I said, unless the point P now in this scenario here also is on the same line, then obviously there isn't anything we can do. So you can see a little bit the geometric interpretation of these epipolar and trilinear constraints in these settings. And this is the key message of this chapter really, is to say that considering more than 2 images, in fact 3 images at a time, will help to better constrain the reconstruction, to assure that there is a unique pre-image, that there is a unique reconstruction. So you see that this multi-view constraint on the rank of this multi-view matrix MP, it allows us to distinguish three different cases. Since this matrix MP has two columns, its rank can have three cases. It can be rank 0 if the matrix itself is 0, meaning both column vectors are 0. It can be rank 1 or rank 2, right? That is the three possible cases for a matrix with two column vectors. And in these cases, we can summarize: if the rank of the matrix is 2, then there is no point correspondence, there is no point in the intersection of the various lines, and we have an empty pre-image, so no reconstruction. And that basically means that if these are really the camera motions that make up that are involved in this matrix MP, then the observations that you have cannot correspond to a single 3D point observed in these images, right? And we're always assuming that there is a point P that we observe in M images, right? And so in other words, the way you can use this multi-view matrix is it gives you information about what camera motions are conceivable. And the idea is that we say, find camera motions such that the rank of this multi-view matrix is 1. Because in that case, we have point, or is bounded by 1, right? The feasible camera motions are such that the rank is either 1 or 0. And in the case that the rank is 1, we have a point correspondence and we have a unique pre-image. Whereas if the rank is 0, then we do have a point correspondence, meaning there is a point in the intersection of the various pre-images, but that intersection is not unique. It's not a unique point in case of rank equals 0. And so how can one use these constraints? We can basically use them to decide which features to match. Basically, we can say find points in the image and correspondences such that the rank of this multi-view matrix is exactly 1. And that allows us to establish point correspondence over multiple frames. And lastly, we saw in the previous slides that these rank constraints on the multi-view matrix can be equivalently rewritten in form of sets of trilinear constraints involving always 3 images of a point and the corresponding camera motions between these 3 images. And we saw that this is really equivalent, and hence having more than 3 images at the same time in a constraint doesn't provide any additional information for the reconstruction, because we have this result that the multi-view rank constraint is equivalent to all these trilinear constraints. And we saw this geometric interpretation, and we saw the various degenerate cases of points observed in 3 images. Now we'll look into the reconstruction challenge. So so in some sense, the multi-view constraint here, these rank constraints, they are the generalization of the epipolar constraint that we had for pairs of images to multiple images. Right? And much in the same way as we derive the 8-point algorithm, we can try to derive a corresponding algorithm for reconstruction of camera motion and 3D structure in the multi-view setting. So 8-point algorithm was for 2 views. Now what would be the analogous thing for multiple views? And this is what we're going to tackle next. So the rank conditions here on the multi-view matrix, they capture all the constraints among the multiple images of a point. And so in principle, one could perform a reconstruction, minimizing some global objective function. We'll talk about that in the next chapter, subject to these rank conditions. And this would lead to some nonlinear optimization problem analogous to what's called bundle adjustment in the two-view case. So it's a multi-view bundle adjustment. And we'll talk about these things in the next chapter. But one can also aim at something akin to the 8-point algorithm, or the analogous thing to the 8-point algorithm, that where we separately estimate structure and motion. And this is what we'll derive in the following such an algorithm. But one should point out that these algorithms are not necessarily very practical. These spectral approaches where you deploy kind of eigenvalue solutions, and they do not imply optimality in the context of noise and uncertainty. Right? So both the 8-point algorithm and the following algorithm for the multi-view setting, they really assume that you're observing m points, n points in m images, and that you have exact observations and exact correspondences. And the key issue is, in practice, you never really have that. You never really have exact point correspondences. Sometimes you have correspondences there, they're entirely wrong, where you're matching the wrong points across images. But sometimes you do match the right points, except that due to the observability issue, they may not be precisely located where they should be. And so there is some uncertainty in the exact location of these points. And the problem is that the way this uncertainty propagates into these kinds of spectral algorithms is not very nice. So it degenerates the reconstruction significantly. But nevertheless, it's possibly interesting to look into this algorithm to see how does the 8-point generalize to the multi-view setting. And so let's look at that. Suppose we have m images of n points, pj. So now, before we had m observations of 1 point p. Now we generalize this, much like in the 8-point derivation. We assume that we are not observing just 1 point, but n points, and these are pj. And these observations, we will call them x1j to xmj. So the observation of point j in the images 1 through m. And what we want to estimate is the unknown projection matrix. The rank condition that we derived earlier states that the two columns of this multi-view matrix NP for every point P are linearly dependent. And if we write that out, here it is. So this is the same as what we had before, except now we always have this upper index j for the various points from j going from 1 through n. And alpha j are parameters, and we'll see that they correspond to the inverse steps from the first images. So alpha j is just 1 over lambda j1, the distance of point j from the first image. So these alpha parameters, they basically correspond to the inverse steps of the point P, J observed in image 1. And you can see that because each row of this above equation can be obtained from just looking at this observation of point J in images, in these images. So these are the equations connecting image observation in the image 1 and the image I. And so this is nice. There is equations coupling the unknown distances of a point from the first camera and the various rotations and translations of the camera. And if we look at this equation, it contains both the camera motions that relate the first camera to all the subsequent cameras to M. It contains the observation of all the points in images to M. And it contains, and the image 1 as well here on the right side. And it contains the inverse steps of the first of every point with respect to the first camera. And now we'll go a little bit in analogy to the 8-point algorithm. We'll assume that we have the depths of these points. So this alpha j, the inverse depths, if we assume we know this one, then what we can do is we can basically solve for the camera motions, right? Because, why? Because then we have an equation here. This is an equation that is linear in the camera motions, R2, T2, R3, T3, etc. And you see that these equations are linear, assuming that all the 2D observations, we have them, that we always have. In addition, we now assume we have the structure parameters, so the distance from the first camera. So you see, at that point, we're slightly deviating from the 8-point algorithm because the 8-point really decouples the structure parameters lambda j from the camera parameters. Here, we don't decouple it, but we assume that one of them is known. So we derive what is called an alternating optimization method, where you alternatingly estimate alpha j and the camera motions. So here, for known structure, known alpha j, we can solve this, we can write this. If we rewrite this, we can basically use this Kronecker product to extract, to basically write this as a matrix vector in this equation here, the one here. If we use the Kronecker product to basically extract R and T here, then we can write all of this in the following matrix vector form, where we always have x11 transposed Kronecker product with xi1 hat times ris, and then alpha 1 xi1 hat ti. Right? And this is then one big matrix. And if we assume the alphas are known and the xi's are given here, then this matrix P is a known matrix. And we see yet again what we, and here, by the way, this is Ri stack is just the stacked version of this rotation matrix, where we stack the 3-column vectors into one long 9-dimensional vector. Right, so this is a vector that contains 9 elements for Ri and then 3 for the translation. So it's a 12-dimensional vector, and this matrix Pi is a 3n by 12 matrix. And now you see that the desired camera motions, they define the null space of this matrix. And we have such equations for all the different camera motions. And then we can say for this matrix to have a non-trivial null space, a non-zero camera matrix or camera vector here in this case, the 12-dimensional camera vector containing rotation and translation parameters. For this to be non-zero, we need this matrix that in principle can have a rank 12. We need it to be rank deficient. There must be a non-trivial null space, so we can impose that this should be at most rank 11. And in fact, for this to have even the possibility to have rank 11, we need, obviously, n must be at least 6. And that's basically because it's 3n times 12, so the rank is always at most 3n. But as we saw, these skew-symmetric matrices, they always only have rank 2 rather than having rank 3. So it's basically, this will be 2, 2n. And then with n equals 6, we can expect the rank could be 12. Um, and so this is why we actually need at least 6 points, not 8 points, but we need 6 points for this algorithm to work. So if we assume that we have at least 6 points, in which case the rank could potentially be 12, then constraining it to say the rank must be at most 11 is a meaningful constraint. In practice, one would typically use more than 6 points to assure that we have a full rank matrix here, and then we compute a singular value decomposition, and as in the 8-point, we will take the column vector associated with the smallest singular value, and that will give us the camera vector for camera I. Right, and so you see, once we have structure, the alpha parameters, the known inverse steps, we can use this to recover the camera motion by singular value decomposition. So again, we can use linear algebra techniques to compute the camera motion. And in turn, once we have the camera motion, we can use this equation here, right? That means then, what is this equation? If we have all the camera motions, Ri, and Ti, then we have these structures here, and then we can determine alpha j by what's called a least squares estimation. You know, this thing should be 0 for all j from 1 through n. And what we can now do is we can do the sum over all j and take the norm of this squared and set and say this should be small. And if you minimize this in a least squares fashion, that's then a quadratic loss function with respect to alpha j. And then you set the derivative with respect to alpha j to 0, then you get a linear equation in alpha j, which you can solve, and this is what this looks like. I apologize that I didn't actually write out these steps. It would be a bit lengthy, but in some sense, you can try that at home. Take this expression on the left-hand side, take the norm of it squared, sum up over all j from 1 through n, and then you say this should be minimal. So you set the derivative with respect to alpha j, you set it to 0, and you get a linear equation system. You solve that for alpha j, and you can find for yourself that this is what you get. Here's the sum from 2 to m of these elements, and then the sum from of these elements. And so that gives us a way to iteratively estimate structure and motion. We can say if we know the structure, the alpha parameters, then we can use an SVD to compute the camera motions. And if we know the camera motions, we can compute the structure. And one way to mimic the 8-point algorithm would be to alternatingly solve for both. And then the question is, if you iteratively solve here, how would you initialize? Well, you know, you can always start with a 2-view setting, make use of the 8-point algorithm for 2 views of these endpoints, and then use the 8-point to compute an estimate of structure and motion, and then use that estimate of the depth values, lambda j, to estimate the camera motions as shown in the previous slide. Right, so you would use SVD to determine the camera motions here. So you would first use the 8-point for the first 2 images, or any 2 images in your set, and get an estimate of the depth values, lambda j. These are the inverse of the alpha j. So alpha j is 1 over lambda j. And once you have the alpha J's, you can use this multi-view approach to compute all the camera motions. And then you can do this alternation to, refine the structure and refine the camera. And this can be done either in batch mode or recursively. And what's interesting is here, the estimation of the structure parameters. If you look at this solution here, this actually makes use of all the camera motions in all the images and all the 2D observations here in the various images from 1 through M. Yeah. Whereas the estimation of the camera motion, it only makes use of they're estimated independently. Oh, sorry, this was wrong. Let me correct this. While the estimation of the camera motion, the projection equations, makes use of the 2 frames 1. And yeah, that's what I said. So this only makes use of the frames 1 and J. If you look into it, you have x1 and then you have xi here. So the observation of the endpoints in 2 images. This one makes use of the observation of the endpoint in all images. Here's then, so this concludes the aspect of the part of observation of endpoints in M images. And we found an algorithm that was somewhat akin to the 8-point algorithm. But you see, in some sense, it's not as powerful as the 8-point algorithm. And that is in the sense that the 8-point is really a closed form solution to get camera motion and then 3D structure. So we can really decouple the problems of motion and structure estimation. In this generalization, we haven't fully decoupled it, in the sense that whenever we estimate the structure parameters alpha j, we need the camera motions. And when we estimate the camera motions here, we need the structure parameters. We couldn't fully decouple things, right? And in that sense, it's in many ways suboptimal as an algorithm for 3D reconstruction. Because first of all, you use SVD, singular value decomposition approaches, spectral solutions. They're called spectral because you're using the eigenvalue spectrum of matrices. And these spectral solutions, this is true for this multi-view reconstruction, but it is typically true for a lot of areas in the sciences. Whenever you phrase something as a spectral solution, a closer look often reveals that you tend to neglect uncertainty and noise in the observations. And so first we have to assume that there is no noise in the observations. And secondly, we still don't get a really closed form solution, but we get something that is iterative in the sense that we alternatingly estimate alpha j and the camera motions Ri and Ti. And so this is kind of a downside that we see of this algorithm for reconstruction of structure and motion in the multi-view setting. It is not as elegant as the 8-point algorithm. So this is for observations of points. We can do the same thing for the observation of lines. And this is detailed in the book of Ma, Suato, Koseka, and Sastry. I have a brief kind of overview of this in the remainder of this chapter, but I don't want to go too much into these details here. So let me just glimpse over it. This is not really, I don't think this is relevant. We'll make sure this doesn't play a role in the exam. But I still, just for your interest, want to brush over it. What you do is you consider, again, observations of a line in multiple images. And you remember when we said a line, we derived that a line has a base point x0 and an offset vector v. And then for both the base point and the offset vector, we have these constraints that basically define this normal vector Li. And so we have this matrix WL here, and we say there are two vectors, namely x0 and v, that live in the null space of this matrix, that are mapped to 0 by this matrix, right? Because we have this for all I, and so we can write that into a big structure, a matrix M by 4 matrix, and this M by 4 matrix contains two vectors, x0 and v, in the null space, and that means this matrix, which could potentially have a rank up to 4, because it has 4 columns, this matrix only has rank 2. Why? Because we have two, in fact, linearly independent vectors, x0 and v, that define a two-dimensional null space. And this is where you see the advantage of looking at lines. Once we have a line that we observe in two images, we have a 2D null space, and that gives us a stronger rank constraint. We can directly impose that a matrix with 4 columns should have a rank at most 2. And then we can also interpret this geometrically. We can look at pre-images of lines observed in two images, and then we see, with pre-images, the idea is that we say for two observations, these lines, the pre-images should intersect. The problem is that if you consider a line, saying the pre-images should intersect is not a very strong constraint for lines, because if you take two planes, they practically always intersect. No matter which line you observe here, the intersection of pre-images is possible. And then you see, if you consider triplets of observations of lines, then it's actually less trivial. Then you immediately see considering triplets of observations of lines and saying these should all intersect in one line is not trivial, in the sense that you can have pre-images for one pair of lines intersect in a line L2, pre-images of the other intersect in a line L3, but they need not be the same line. And this is where multi-view constraint can help, because you impose that the intersections of, there should be a non-empty intersection of all three pre-images in a single line, as shown here. And that gives us a unique reconstruction. So going back, what we do in a multi-view setting now is quite an analogy to the point observation. For the line observation, we have this matrix that we said has rank at most 2. Then we again pre-multiply or post-multiply here from the right-hand side with a full rank matrix like this. We derive this matrix, and then again we say that, this for this to have at most rank 2, since this contributes a rank 1, it's a column vector here. This submatrix can have at most rank 1, right? And this is how we compactify this constraint quite analogously to the point observation. We can derive this submatrix down here, this one that contains the camera motions for all the images and the observations of the lines, with encoded in these vectors L1 through Ln. And that forms a matrix that has 4 columns again. And this matrix with 4 columns, now our statement is the rank must be at most 1. And basically, the statement is that a meaningful pre-image can exist if only if if the rank is at most 1. And then we can derive trilinear equations. Again, we can make use of the fact we can basically derive trilinear equations of this form. I don't want to go too much, as I said, into details, but you can derive similar kind of trilinear equations that always couple what? They couple the observation of a given line in 3 images, namely image 1, image I, and image j, and the corresponding rotation matrices Ri and Rj. Interestingly here, these trilinear equations do not contain the translation vector. But then taking into account the full kind of multi-view matrix and also its 4th column, we can derive these trilinear equations that involve always triples of lines and rotation and translation. And so basically we have 2 constraints that we can derive, one that only contains the rotations of this matrix, a trilinear equation that only constrains the rotation, and another one that constrains both the rotation and translation. And that is in fact from the same lemma with this two-column matrix having rank 1, you have the same trilinear constraint. And so we have this lemma given 3 camera frames with distinct optical centers and any 3 vectors, L1, L2, L3, that represent the 3 line observations in the 3 images. Then these 3 images satisfy the trilinear constraints that we had. Then if these trilinear constraints are satisfied, then there is a unique line in the intersection of the pre-images. Right, then we can basically say this: if this trilinear constraint is fulfilled, then we have a case like this one where there is a unique line in the pre-image in the intersection of these pre-images. So we can basically rule out this case where the pre-images do not coincide in a single line. That can be ruled out by these trilinear constraints. So again, we see that just looking at pairs of images is not sufficient. Even in the case of line observations, for looking at pairs of images, we cannot assure that the pre-images coincide in the same line, but once we consider 3 images at the time, then we can assure that there is a unique pre-image. So to summarize, we have much the same as in the case of points. We have that in the case of lines. So this is the case, the section on multi-view reconstruction of lines observed in M images. We can see that if we observe M lines in M images, so a line in M images, and this line is associated with these vectors Li that are normal to the pre-image and normal to these lines in each image. Then they correspond to the same line in space if the rank of the matrix ML relative to any of the camera frames is 1. And if the rank is 0, then we have a pre-image, but then we have a line, but it's determined up to a plane on which all the camera centers must lie. And so overall, we have these 3 cases. The rank of this matrix there are 3 possibilities. It can have rank 2, rank 1, or rank 0. In the case of rank 2, we have no line correspondence, meaning there is no meaningful reconstruction. In the case of rank 1, we have a correspondence and a unique pre-image, i.e. a unique reconstruction. And in the case of rank 0, meaning the matrix ML itself is 0, we have line correspondence, but the pre-image is not unique, meaning there are multiple conceivable reconstructions. So here's the summary both for lines and points. we can define a set of matrices. We saw it, and this is similar in the line case. We can define matrices NP, WP, and MP, and then we have corresponding rank constraints. And so by simultaneously considering M larger or equal to 2 images, so 3, 4, 5, 2, 3, 4, 5 images, we have constraints that tell us when is there a reconstruction conceivable. And so these rank constraints, they generalize the epipolar constraint that we had in the case of 2 views. They generalize these epipolar constraints to multiple views. And they assure the existence of unique pre-images. So by saying the rank should be exactly 1 for this multi-view matrix, either for a point or a line, we can assure that there is a unique reconstruction. And when I say unique, again, always unique up to scaling. Obviously, you can always rescale the world and everything by a factor, and you'll get the same observations. And we also saw that these multi-view matrix and multi-view rank constraints not only allow to provide a unique pre-image, a unique reconstruction, but they can also serve as a basis for an algorithm to actually reconstruct camera motion and 3D structure. An algorithm much akin or analogous to the 8-point algorithm, but the key difference was the 8-point is a single-step algorithm. In one step, you get the camera motion relating the 2 images. Here, we saw that all we can hope for is an alternating algorithm where we alternatingly estimate camera motion and 3D structure. And as such, these iterative alternating optimization methods are usually not as good as a single step closed form solution.